Okay, so the last thing that we sort of stopped at yesterday was this problem with Coq having to prove the termination of fixed points, and how n minus 1 happens to be a larger term, right, than the original argument n. And hence, as a result, Coq is not able to show that this function will terminate. And it is, since it is using this metric, a very simple, um, although approximate way of saying which functions will terminate, we have to use this other mechanism, right? Other way of defining sum2, where we pattern match on the underlying constructor. And this went through. So we have our sum2 definition. So this sum2 of n just says that it's the addition of 1 plus 2 plus 3 plus up to n. Actually 0 plus 1 plus 2 plus, but that doesn't matter. Okay, so now that we have the sum2 definition, let's look at how we might actually prove the summation theorem that we want to prove just using pen and paper proof, right? So we are going to use induction. We want to prove that for all natural numbers n.
Sir, I have a doubt.
Yeah.
The previous.
Yeah. Oh, sorry. Yeah.
So the length of sum2k is same as the length of sum2n, right? So how does Coq know that this?
Yeah, okay. So good question. So the way it looks at termination is, if you have it's actually a really good question. So if you have a inductive type, right? The way inductive types are defined is there is some base case for the construction of inductive type, right? And then there is the inductive cases, essentially. So there's a case where you sort of say, use a smaller structure of the same type and build on top. So the type of natural numbers, right? If you print nat, it's the case that when you destruct a S constructor, you have a natural number within it, and by definition, we are not allowing recursive values and such in Coq. So by definition, this natural number is smaller than the natural number S of nat, right? And what that means is that by definition, by construction, because we are only allowed to construct inductive types that way, n, we know, is structurally larger than k, because k happens to be a subterm of n. And hence, since we are actually recursing on k here, we know that the next time we go here, it can either be 0, in which case we terminate, or we are going to destruct k again to get a sum k prime, right? And k prime will be smaller. So terms can only get smaller so many times because of the way inductive types are constructed. And that's the reason why Coq is able to say, okay, I know this function will terminate. Does that answer your question?
Yes, sir.
It's a really nice question because it happens to be, it comes from the fact that how inductive types are defined in Coq, because we have a base case and inductive case. So you can essentially recurse on any. So we have this term called structurally smaller. So we call k to be structurally smaller than n, right? Because we know that k is a subterm of n, and this applies for all inductive types. Any other questions on this? I think we decided that we will spend a minute or two discussing this. Any other questions on this? Yeah, Hashin?
Yeah, so in this case, right, we were able to kind of work around that restriction of the term being syntactically larger by making use of this property of a successor, which the natural type has, right, as per the definition. But will we always have some workaround like that? So where I'm coming from is like, so let's say hypothetically you had a function where you want to recursively find the power of a number. Like for example, you had 16, and the 2th root would be, let's say, 4, right? So 2 power 4 is 16. So there you would naturally keep dividing by 2 recursively, right? So you'll have n and n by 2, and n by 2 is obviously syntactically larger. So is one of the challenges here to come up with workarounds in such cases, or is there something else to do?
Yeah, so I think that's one of the challenges as well. A better example that we've sort of recently have been doing with one of my PhD students is doing a DFS on a graph, right? So you're starting from a root node. Maybe there is a dedicated route, and you're doing a depth first search. And we know that if you recursively do depth first search, it will terminate, right? But we can't have an inductive definition of a graph. You cannot write because graphs can have cycles, right? So you cannot write an inductive type for a graph in Coq. Coq would just not allow it because its graph is not an inductive data structure. So one thing you have to sort of do is you have to have some other way of expressing to Coq that when you do this recursion, when you do this depth first search, you're always getting smaller. Coq has other ways of expressing this, getting smaller. So in F star, we will see that very explicitly. So you can say that when you recurse on say the graph, you will say something like maybe you're doing. So the way you do DFS is you sort of go down a path and then you mark everything as visited, right? So that you don't keep going down the same path again and avoid cycles and so on. So you'll say that the number of nodes is equal to actually what was the termination condition? So we will have to say something like as we go down traversing the graph, the number of visited nodes will keep increasing, and that can never be larger than the total number of nodes. And because it is climbing up to the total number of nodes, we can express to Coq that the function will terminate. I mean, details are there, but that's the sort of reasoning that you have to use to convince Coq. Coq has certain mechanisms to say you can provide a total function and then say, here is the decreases metric. Here is how my function is decreasing. And Coq will take that and just accept your function. Yes, that is certainly one of the challenges. Because when you have to prove things, right, essentially termination is an effect. So if you are, I mean, this sort of is a digression, but a useful digression. When we call pure programs, right, in OCaml, we saw that pure program means we are not using references, but really the real mathematical definition of a pure program or a purist notion of a pure program will not also include non-termination. So if you have an infinite program, then we would call that program an impure program because it has divergence. Essentially, it doesn't terminate, right? So if you look at the sort of programs that Coq allows, those are really pure programs in the sense that they don't have side effects. Side effects include writing to references and arrays and so on, but also they actually terminate. So the Haskell notion of pure, right? When Haskell says, oh, it's a pure functional language, Haskell's purity includes non-termination. So it is all a bit muddled, but really when you want to do proofs, you really want to also show that the functions that you're defining, the properties that you're using, right, so are actually terminating. It's certainly a challenge. But if you sort of always try to express your terms through inductive types, which is what the most useful structures that we want to reason about will have. I mean, graphs are a special case. You can make it go through. It's not going to be a problem most of the time, as we will see, right? We won't ever have to fight this property over and over again. There will be some places where we might have to do something, but generally it won't be a problem because naturally the only way of expressing data in Coq is inductive types. So by definition, if you recurse on a smaller subtype, things will go through. Anyway, some digression, but that should sort of give you some idea of where these ideas come from and how it fits in the real world. Okay, any other questions, comments? Okay, in which case, let's continue. Okay, so yeah, so this is the inductive definition of the summation formula. So we are going to show that sum2 of n, which is the function that we define, is the same as n times n plus 1 divided by 2. By induction on n, we have to prove it for the base case. Right? If you substitute 0, you will see that both of the sides are reduced to 0. For the inductive case, you assume you have to show that the property holds for k plus 1, assuming p of k holds, which is this term, right? Sum of k equals sum of, k times k plus 1 divided by 2. If you do the substitution, you will have to do algebraic reductions, right? So you simplify the definition of sum2, right? And you can do one step of the reduction. This is basically applying one step of simple. So you get k plus 1, sum to k, and you get some term here. And at this point, you can apply the induction hypothesis, right, to get rid of the sum2. So this term can be replaced with the right-hand side of the induction hypothesis. So you can replace that with this one. And now if you do algebraic simplification, you get the same term on both sides. And this goes through, right? There is no problem there. On paper, you don't have to think a lot to convince yourself that this is how things are going to work out. But if you do stuff in Coq, you will obviously encounter a lot of tricky issues. So let's do the proof in Coq. So we are going to start with the same theorem, right? So whatever I've written here, sum to n is n times n plus 1 divided by 2. So I've got that here. So let's start doing the proof. So you do the introduction. We are going to induct on n, right? The first case is trivial, right? So you do simplification. I'm not even showing simple here, but if you do simple, you'll get 0, 0. So trivial makes it go through. And in the inductive case, as we saw here, right, in this step, you can do one step of simplification. So if you simplify, it actually expands to, it simplifies in a lot of places, right? And in particular, what has happened is this divided by 2, right? If you sort of stare at it, we are using natural number. So this, when you divide a natural number divided by 2, you have to do integer division, right? 3 divided by 2 is 1. And formally reasoning about 3 divided by 2 equals 1 involves some other things, right? So you have to sort of say, oh, there is a remainder, and you have to sort of take care of the remainder and so on. So it's not straightforward division there. And we don't know, right? So actually, so it's the reason why you can always divide by 2 this number is that it's the product of two successors, right? So essentially, if one is even, the other one has to be odd, right? So these are all the implicit things that are under works here, right? That is why we don't end up with a fraction when we divide by 2 this number, because we are multiplying n and n plus 1. I mean, n plus 1 and n plus 2 here, but one of them has to be an even number, so you can divide that number by 2. All of this is sort of in our mind, and we know that this works. We know algebra, we know all of this works, but these are all proofs that we have in our mind, right? We have to sort of communicate all of this to Coq, and that becomes tricky, right? So when you simplify this, what you end up getting is this div mod, and you can sort of think about this as division modulo, right? Integer division, and it gets tricky, right? So you can do the substitution, which is sum to n. You can do this rewrite using the induction hypothesis, just as we did here, right? We had the induction hypothesis here, and we did the substitution. You can rewrite it, but yeah, reasoning about this is going to become a little bit tricky, right? So it is always useful to avoid reasoning about integer division in Coq because of all of the things. I mean, you really have to show that one of them is you're going to get an even number, right? And that's why you don't end up with a fraction and so on. So we are not going to go down this proof the same way, right? So we are going to abort. This is with good reason, right? So of course you can go ahead and prove it using all of the things that you might know about natural numbers. So one of the tricks about doing proofs is um, the first idea that comes to your mind for proving things is not the good idea to go down with, right? So you sort of have to think about, okay, how can I make it simple so that my proofs go through? And a good metric for the proof burden, we call it the proof burden. Essentially, you have a theorem, you're proving stuff. So the number of lines or the amount of effort that you have to put in to prove, say, X lines of code is in the industry, right? It's about 10x, right? So this is the state of the art today, right? If you have to sort of say, okay, I have a program which has a 1,000-line program, then I'm going to write a proof for it. You will often see that the papers will have 10,000 lines of proof accompanying 1,000 lines, right? The way you have to see this is observe this one. Sum2 has a definition which is also small, right? But if you start writing the proof, we are reasoning about it in a complicated way. So proving things is always going to be expensive, right? So a clever, but it's actually an art, not very scientific, right? Because there are given a theorem, there are lots of different proofs that you can provide. It's an art to actually identify like a simple proof, right? And elegance comes from being able to discover that simple proof. Of course, you can do this in Cork the hard way, and then get some Cork to accept your proof. Even if no one is looking at it, just because you prove something doesn't mean there is value in it, right? If you prove something using a clever technique, then it actually you get insight, right? You get some insight about the problem that you're dealing with, and that is what like theory people really care about. I mean, there is some value in it. I mean, even though we are in the business of just saying, okay, I write programs, I want my programs to be correct. I don't care about the proof. There is always some value in like thinking about, okay, how do I approach this problem, right? How do I avoid going down complicated paths? And we are going down complicated paths here because of this div mod. So, so one way to sort of simplify this is to say, instead of proving this directly, right, multiply both sides by 2 so that you avoid the division, and then we can come back to handling division separately rather than handling the full complexity here, right? That is what we are going to do first. So, so we define a different theorem, which is sort of taking this theorem and multiplying both sides by 2. We call it sum of sequence, no division, right? 2 times sum to n equals n times n plus 1, right? So if we can do the same thing here, right? So do the introduction, do the induction. First case goes through very simply. Second one, we see that we have a induction hypothesis where you have the term 2 times sum to n, right? So in order to apply this rewrite rule, the term has to be the same, syntactically the same, right? So the thing that we have here, which is where we are going to apply eventually, is 2 times sum to s of n, right? So naturally we can think that, okay, I will do simplification, and then simplification will sort of allow me to do the substitution. So what happens if you do simplification? Oops, simplification has actually gone too far, right? It has gone ahead and reduced a lot of the term too much. So what we were looking for is a term that is syntactically equal to this one. But because Coq knows how the definition of what is the definition of sum to, it has gone through and gone as far as possible it can, and it has reduced too much, right? So observe that this is the same term, right? We've just simplified, but we cannot do this substitution anymore, right? We don't have a term which is the same as this one. We have sum to n and plus and other terms here. So this is unwieldy, right? So this is one of the things that you will encounter with Coq. So if you sort of say go and do the simplification, it might just be very aggressive, right? And the problem here is simple is a tactic which is a bit too aggressive in reducing all the way through, and it is preventing us from applying this induction hypothesis. So what can we do here? We can have a look at this one, right? So what is this term? It's 2 times sum to n plus 1. And if you do one step of simplification, you will get 2 times n plus 1 plus sum to n, right? That is precisely the definition of sum to. And you multiply, you basically distribute the multiplication over the addition, you will get something like this, right? So 2 times sum to n plus 1 is 2 times n plus 1 plus 2 times sum to n, right? If we get this term to reduce to this term, then observe that this term here is syntactically the same as the term we have on the left hand side of the induction hypothesis. So we can then substitute n times n plus 1, get rid of sum 2 essentially, so that we can then go ahead and prove it, right? So because this is a specialized step that we are adopting, the way we typically do this is to define a helper lemma, right? So observe that we have a thing called lemma here, which you know what lemmas are, right? They are sort of like auxiliary things that you know about a particular proof, so that you can use it in a theorem. In Coq world, right, there is no difference between theorem and lemma. So lemma is just alias for theorem. But for humans to actually read it, whenever you see lemma, you sort of in your mind identify that, okay, this is some helper thing that is going to support a theorem, right? That is the implicit assumption that we have. So yeah, so what we are going to do is to help us go from this step to this with the help of this lemma. We call this some helper, okay? And that's the first thing. So we are going to define a lemma. And the second thing that we are going to do is to use this new tactic called ring in Coq. So you know what rings are, right? Rings are these algebraic structures with a zero element, a set of other elements, a unit, and some notion of addition and multiplication. Essentially, they have nice properties that addition is commutative, multiplication is commutative, and multiplication distributes over addition, and so on. I mean, these form algebraic structure. I think you would have studied this in discrete math or even earlier. Natural numbers with addition and multiplications form a ring. And Coq has very good tactics for solving equations, right? Proving equality with terms that involve natural numbers and additions and multiplications. It comes in very handy so that you don't have to deal with commutativity and multiplication and distribution of multiplication or addition explicitly, right? So Coq knows how to do it. Actually, ring works on all algebraic structures which have the ring property, and natural numbers with addition and multiplication have the ring property. I mean, they form a ring. Everyone knows rings, right? So if you don't, you can just Wikipedia this page, right? So I think rings are actually quite fun. I mean, one of the things with these sort of, I mean, in programming languages, right, we try to take complicated problems, reduce it to nice, well-known mathematical structures which have good properties, such as rings. And given that rings have nice properties, a lot of the proofs and reasoning becomes simpler. Natural number reasoning over rings is one, right? So we are trying to prove some complicated property. Given that we know how rings operate, we can just use the ring tactic to make this thing go through, which is what we are going to do. So let's go through this step by step. So we are taking this term, right? And we are going to show that this term is the same as the term here. Just simplify it one step and then multiply it, distributing multiplication over addition. That is all we are doing, right? This is elementary math, but we are teaching Coq how to do this. So we have this new lemma here, right? We do the introductions, you can do the simplification, and then all we are doing is we are just going to appeal to the ring tactic, because this involves like additions, right? Whenever you see an s, you see plus, you think about +1, and there is +0. There are some unknown constants, right? We know n is a natural number. There are also some unknown functions. So there is sum to n, and the thing that you know about sum to n is it's a function, right? And it takes a natural number, it returns a natural number. So as long you can sort of treat this sum to n as just a constant value, in a sense that it behaves like functions, right? If you give the same n, it returns the same value. So when you look at structure of say goals which involve just additions and multiplications, right, and things on equalities, then you can use the ring tactic to make the whole proof go through. You don't have to look at the details, right? So it's a bit complicated, but we have a reasonable assumption that ring will make this go through. So you just do ring. So we proved it. So ring has helped us prove this complicated math thing that we just saw. Okay, so questions on this. I've been talking for a few minutes now. Anything, any observations, questions? Okay, interrupt me, right? So if I keep talking, you can always say that's not at all clear. You're just talking nonsense, right? So, and then I'll sort of think about what I'm saying. Okay, so we aborted here, right? So we were trying to prove this theorem. We aborted here. So let's go back to proving that again. So we do the same thing as earlier. Induction, base case is trivial. Here, when we come to this case, right, here is when we did simple and we oversimplified everything. It was no longer possible to apply the rewrite from the induction hypothesis. So here, because we have this lemma, right, that this term is equal to the right hand side term, we can basically use the rewrite tactic to apply the lemma. So a lemma which has been proved is very similar to having something in the assumption, right? It's the same thing. So you can do this rewrite. So what this rewrite does is it basically looks for a term which has this particular structure, which is this term in the goal, and then replaces that with the right hand side term, right? So when you do this, we have what we expect, right? We have the right hand side term. Now we can apply the induction hypothesis. So observe that there is sum to n, 2 times sum to n, 2 times sum to n. So you can apply the induction hypothesis. Again, these arrows are not necessary, right? Because by default, it applies left to right. And now you have a term which involves multiplication, additions, constants, right? And yeah, so this is a structure which ring can prove. So you just appeal to ring and we proved it. So what have we achieved so far? So we have proved that 2 times sum to n is equal to n times n plus 1. So we have to go back to our original goal, right? Which was sum to n is n times n plus 1 divided by 2. So that is what we have to show. And for that, we have to appeal to another lemma, which says something about divisions. So let's read this division helper lemma, right? The goal is to bring this times 2 down here, right, to the right hand side. So what is the saying? It says that if c is not equal to 0, assume that there are 3 natural numbers a, b, c, right? If c is not equal to 0, then c times a equals b. If you have c times a equals b, then it is the same as a equals b divided by c. We are just bringing the c down, right? And we can do that only when C is not equal to 0. If C is 0, then we cannot divide by 0. That is meaningless, right? So that's the reason why we have this precondition here. Okay. I mean, again, this is basic algebra, right? We know that this is just a this is a fact that you get taught in school, right? Oh, here is the reason why. I mean, take my word for it. Oh, you can see examples. Here is why it works. In Cork, we have to actually prove it, right? If we are to use it, we have to prove it. So let's do the proof for this. So we do the introductions, right? The introductions are A, B, C. This this assumption, which is C not equal to 0, and the other assumption, which is C times A equals B, right? So all of that goes up, and then the thing that we are going to do is we are going to rewrite B, right, using this equality assumption. So we are going to replace B with C times A. So let's do that. Okay. So if you sort of stare at this proof, right? I see something which is A. I want to show A equals C times A divided by C. I mean, in pen and paper, you just cancel the C, right? And you'll say, oh, A equals A, and hence proved. But in Cog, you have to go step by step. In particular, the way to read this term is it's C times, and there is an implicit bracket here, right? So Cog doesn't know that it can cancel these things out. And this is sitting outside, right? So the first thing you have to think about is swapping these terms, right? We know multiplication is commutative. So when you have multiplication here, you need to commute these terms so that you get A times C divided by C. And then you can cancel these things out, C and C, assuming that C is not 0, right? If C is 0, then you can't just cancel out because it will be 0 divided by 0. But we have an assumption which says that C is not equal to 0, right? So I'm just going to show you two tactics, right? I'm just going to apply those tactics, which will make it work. I'll then show you how to search for those tactics. So the first tactic says that multiplication is commutative. So multiplication commutes, right? C times A becomes A times C, right? And then the next tactic says div mul, which is that you can cancel things in the numerator and denominator, assuming that C is not equal to 0, right? So we are going to use that rewrite as well. And what you have, we've cancelled that out. So we have A equals A. So that is trivially true. And this is the side condition for doing this cancellation. So you have to show that C is not equal to 0, which is what we show here. So this lemma has been proved, right? But how did I go from here and then identify the correct lemma that I wanted to apply, right? So this is sort of, I just picked it out of thin air. Of course, you can't remember all of the proofs and lemmas about everything, right? That would just be quite an impossible task for anyone to do. So Koch has this nice search technique for looking for proofs. In particular, when we were at this stage, right? We saw that there is a term on the right hand side which is C times A divided by C, and we wanted to cancel out C and C. So we wanted to search for all the theorems and proofs in the standard library that might help us do this, right? So Coq has this nice search command which can take wildcards, right, for actual terms, and then you can fill in the operators that you want, and you can search for all the theorems and proofs that have been in the standard library, which can help you do this, make progress on this, right? So when you do the search, I mean, it finds a lot of things, right? But the first one is what we want. We have div mul, right, which says that for all AB, if B is not equal to 0, the denominator is here is not equal to 0, then A times B divided by B is equal to A. You can cancel out this B and B, right, which is what it says. Okay, so that's good. So we know that we can use this theorem to cancel things out. But if you observe the shape of this, right, it is A times B divided by B. But what we have here is C times A divided by C. So A and C are in the wrong positions, right? We need to commute these somehow. Again, you can search for theorems that show that multiplication is commutative. So here is the search again, which is using, which is essentially searching for, give me all the proofs which have the structure where you have multiplication on the left and right and equality in the middle. And there might be multiple proofs, theorems that satisfy this pattern, and one of them should be commutativity, right? If it does exist. And yeah, so if you do this, you see that there is mulcom, right? Which is n times m equals m times n. There is also other things, right? So associativity, shuffle, and so on, multiplication. So all of these are useful, but what we are looking for is this pattern, right? Nat mulcom, which shows us that for any two natural numbers, multiplication is commutative. And this is how we searched for Nat mulcom and div mul, right? So Coq has this nice system for searching through proofs. And yeah, it searches through all the proofs that are in context, right? So if you implement your own library with lots of proofs, when you do a search, it is searching through all the context. And that's quite powerful because sometimes um, finding the right proof to finding the right theorem to apply is a challenge. And if it is already proved, you have to search for the right pattern. Okay, so we've done that. Any questions on that one? None? Okay, so let's continue. So now we are finally there to prove what we wanted to prove. Okay, so we are now proving sum to n is n times n plus 1 divided by 2. So we do the introduction, right? And then we are going to make this formula into a form which is multiplying 2 on both of sides, right? We are going to use the div helper to do that. So we have a divided by 2 here, right? And we are going to convert it into this form. And if you do that, you get this obligation as well. You have to show that C is not equal to 0 and C here is 2. And we know 2 is not equal to 0, right? So that is what we are going to get. So I am applying div helper, right? The reason why I'm applying div helper is I'm doing backwards reasoning, right? There is a P implies Q implies R, right? I'm pattern matching on this one, which is this term, actually the whole term. So I'm going to get two things that I need to prove, right? I need to show that P holds and Q holds. So if you apply div helper, you get two sub goals. That's the reason why you get two sub goals. We can show that 2 is not equal to 0 by discriminate. This we saw in the first lecture, right? We use discriminate to discriminate the days of the week. And we can use discriminate here because natural numbers are also inductive types. So that goes through. And for this one, this is the theorem that we had proved earlier, right? Sum of sequences, no division. So you can just apply that theorem to rewrite the term. So if you rewrite it, you get n times n plus 1 on both sides, and this trivially goes through. So finally, we have the proof, right? We had to work through lots and lots of steps and search through theorems and come up with interesting ways of expressing this, but we have a proof. So take this as an illustration of what is needed in order to do simple proofs in Coq. And again, the way you should think about it is um, simple things are difficult. Difficult things are also at the same level of difficulty. So it's not going to get terribly difficult working with proofs this way. But just because we are being very precise about how these numbers and arithmetic and everything is done, so you have to be very explicit about things that you do in Coq. Okay. Questions on that? No questions. Okay. So okay. So yeah. So we are doing all this work, right? And I said that we want a world where we can sort of write software which is sort of has some mathematical properties, right? So, you prove some property about a software, and now you deploy the software. But we've been programming in Coq all the time, right? And as you've seen, Coq is sort of this weird language which we cannot actually run these programs in the real world. So Coq has this very nice mechanism called extraction, and the idea is this, right? So you write some code in Coq, right? And this can be in this Coq's own functional language. You write some theorems and prove that the code is correct, right? And what you can do then is to extract the original code that you have proved theorems on into some language. You can extract things to OCaml, or you can also do extraction to Haskell and Scheme, right? So this extraction is very useful. This is how very large software pieces have been built. So there are lots and lots of software which are like formally proved and extracted to OCaml. So and then when you have OCaml, it's as good as any programming language out there, right? So you just run it wherever you want, and the guarantee that you get is that extracted code satisfies the same property of the original code, right? Because you prove properties on it. So in order to illustrate this, right, let's do one more example. So what we are going to do here is we are going to take the classic definition of recursive factorial, right? And then what we are going to show is that this factorial has the same behavior as a tailed recursive factorial, right? Where you have an accumulator and you sort of use the accumulator to accumulate the result, right? And the way you should think about this is the recursive factorial is a specification, right? And you are proving that the implementation, which is maybe has some additional properties over the specification, right? The tail recursive factorial has this nice property that it will not stack overflow, right? And it is very efficient, as efficient as writing a simple loop for a factorial. And what we are proving is this implementation behaves the same way as the mathematical definition, which is non-tail recursive. Right? That's the takeaway here. This is true with very large pieces of code as well. So you need a specification, you need an implementation, which has some additional properties, and you sort of say the specification matches the implementation. When I say match, we are proving equality here. The match might not mean equality elsewhere. We will look at other ways of matching, right, in this course. When we look at it, when we look at other things later. But now we are just doing matching. So we are going to say that for all values of n, whatever the result of factorial that you get from this function is the same as whatever you get from the other function. So let's look at those functions, right? So factorial function, if n is 0, then 1. If n is some k plus 1, then it is n times factorial of k, right? So that's the usual definition. And the tail recursive one, all it does is it has an accumulator, right? And if n is 0, it just returns the accumulator. If n is k plus 1, then you recursively call factorial tail rec with k and n multiplied with the accumulator, right? And the initial accumulator, you just give it as 1. So that if n is 0, then you get 1. Otherwise, you keep multiplying in the accumulator and you get the result out finally. So what we want to show, right, is to show that for all n, right, factorial of n, this implementation is the same as factorial of tail rec of n, right? This implementation. Okay, so why am I showing this? I'm showing this for two reasons. One, I'm going to show extraction. The second, I'm going to show something about more things about proving things, right? So we'll see not new tactics, I believe, but different ways of using tactics. Okay, so how would we do this? So this is a definition, right? So this factorial tail rect takes an n and simply calls factorial tail rect prime this implementation with the same n and 1. So if it is a definition, you just unfold it, right? Keep this in mind, right? So whenever you see a definition, unfold is the tactic to use to expand it. When you unfold tail rect n, right, all you get is the call to tail rect prime n1, which is what we expect because that's the definition of tail rect. And I mean, as you should, right? Let's prove this fact by induction on n. So do induction. This case, if you simplify, you will trivially see that it's 1 equals 1, right? And in the second case, assuming that fact of n is the same as fact of tail rect prime n1, we have to show that fact of n plus 1 is equal to tail rect prime n plus 1, 1, right? If you simplify, I mean, some simplification happens, then you have this fact n term here, right? And the fact n term here. So we can sort of rewrite all of the fact n's in this term with this term, right? That is what I'm going to do by using the induction hypothesis. So I'm going to rewrite it. I get some term here, right? So if you sort of stare at this term, this is obviously true, right? So if you look at this one, what do we know about this accumulator, right? So whatever value that you compute, you're just going to multiply that with this accumulator value, right? This is the accumulator that flows in here, and for any n, you just multiply that accumulator, right? And essentially, this is the same as having. So what is this term? This is just n plus 1, right? So this is the same as n plus 1 multiplied by fact tail rect n1. So, and you distribute the multiplication over the addition, you will get this term, right? So you can sort of stare at this, and that is true. But the fact that the property that if you have an accumulator which is not 1, right, and you compute the fact tail rect prime of n, that is the same as accumulator times fact tail rect n1 is not a fact that Coq knows. It cannot derive it because if you simplify it, right, there is no way to simplify this because the way fact tail rect is implemented is by pattern matching on n, right? And we have some n here, which is just a natural number. It's an arbitrary natural number. So simplification and all of that is not going to work. So really, what we want is we want a way to sort of say, given any accumulator, right? If you compute fact tail rect prime n accumulator, that is the same as accumulator times fact tail rect prime n1, so that we get the same term on the right hand side, right? So this is when you get stuck here, this is the place when you have to say, okay, I know this is true. I cannot make progress here because n is abstract, right? So n is just an arbitrary natural number. So let me implement a separate lemma, right, which proves this fact. Okay, this is precisely what we are going to do. We are going to say, so here is the lemma. We're going to say fact tail rect prime n accumulator, right, is equal to accumulator times fact tail rect prime of n1. And we know this is true, right? The first thing that you do is you either return the accumulator here or you multiply the accumulator. So it has to be true. But you have to use induction there to prove it. So so we've separated that out as a lemma. So now let's prove this one. So I've aborted this one at that point because we cannot proceed. So here is the proof for this lemma that we have. So again, you do the same thing as before. You introduce n and you do induction on n. So one thing to notice here is I'm not introducing accumulator here, right? So I'm just introducing n and I'm actually inducting on n. This is important because it is going to give us the right induction hypothesis. Okay, so we'll see why that is the case. So the key thing to notice is I'm not doing this, right? Actually, I have to do intros and accumulator. So I'm not doing this, right? I'm only doing introducing n, and I'm not introducing the accumulator. I'm keeping accumulator as general as possible. That's the way you should think about it. The reason will become clear in a moment, right? So apply induction on n as you should, right? Now introduce accumulator, pick arbitrary accumulator, do the simplification, and yeah, this is basic arithmetic. So ring tactic will make it go through, right? So observe that in the induction hypothesis, because I didn't introduce the accumulator here, the induction hypothesis actually includes a for all accumulator NAT, right? We haven't seen this sort of representation before. It comes in quite handy, as we will see right now. So now you introduce the accumulator, right? This is going to take this accumulator here, and it is going to move it to the assumption. Do the simplification, right? And what do we know here, right? So, so we have a tail-rake prime, right? N. Some, you can sort of think about this as some accumulator, right? And what is the induction hypothesis I have? I have for all accumulators. I don't care what the accumulator is. If you have tail-rake prime n accumulator, then it is the same as accumulator multiplied by fact tail-rake prime n1, right? So what I'm going to do at the high level is I'm going to take these terms out and replace that with 1, right? And I'm going to take this out, and this will become essentially accumulator multiplied by fact tail-rake prime n1. And the reason why I actually did not introduce accumulator earlier is that I'm going to apply this rewrite tactic in two different ways, right? So whenever you have a for all, it's the same as a function, right? It's just a function that takes an argument accumulator. So I'm going to apply rewrite twice in this goal. So one where the accumulator is accumulator times SFN, the other where the accumulator is n plus 1. So these are two different instances of the accumulator, right? So the way I'm going to actually do this is to say, take the induction hypothesis, right? Because this is, you can read this as just a function argument. You have a for all accumulator, as we have seen in the logical lecture. When you have a for all, go back to how we encoded implication, right? Implication is just a for all. So the way to read this is just a function that takes an accumulator. For the first rewrite, I'm going to use this term as the accumulator. So I'm going to do a rewrite rule. I'm going to take the induction hypothesis here, because it has a for all. I'm going to pick a concrete accumulator, which is this one, this accumulator. And what this step is going to do is to specialize this induction hypothesis where the accumulator is accumulator times n plus 1, right? And when you do the substitution, only this term will get substituted. Okay, so that term got substituted and you got tail-rake prime n1, right? And the second time, I'm going to pick this term as the accumulator. Again, this is a function, so I'm just going to do function application there, right? When you do the second rewrite, the second term is getting substituted. This term also has become n1. This is the shape that we want, right? Because we have the same shape here, and the rest of the things are just standard arithmetic. So at that point, ring will make it go through. So you do ring, and this is completed, right? So the key point to take away here is this delaying the introduction of the for all argument for a particular reason. The reason is that I wanted to use this accumulator in two different ways, right? So my recommendation for you is to introduce the accumulator here, right? And then see how you can proceed with the proof. You will see that you will get stuck somewhere. So do that as an exercise, right? And the other thing that you learned in this lemma is that you can treat these induction hypotheses as functions, right? When you have a for all, it's just a function. So you can specialize it with a concrete term, right? All of this accumulator and S of n is in scope, right? We know n is in scope and accumulator is in scope. And that's why I'm able to use these variable names here. Okay, so now we can actually go ahead and prove our theorem, right? So we have this same thing. Fact of n is fact of tail-trick of n. So we aborted the last time, right? We stopped last time. So let's see. We do the unfold, right? Induction on n. So that's fine. First case trivially goes through. For the second case, you simplify it. We were at this stage, right, where we had the accumulator argument here, and we wanted to get this out. And that is what we are going to do thanks to the rewrite using this lemma. So when you rewrite using this lemma, it is going to do this transformation here. So S of n plus 0 times comes out, right? S of n plus 0 comes out, and you are just left with this term. And now you can rewrite it, right? So you can take this term and use the induction hypothesis to rewrite it this way here. So you rewrite it from right to left using the induction hypothesis. And all you have now is a algebraic equation using multiplications and additions. So ring will make it go through. So what have we done here, right? We've just proved that factorial of n is the same as factorial of factorial tail-trick of n, right? We have proved that fact. I'll stop here, and the last thing that we will see tomorrow is actually extracting it. It's a very simple technique. You can quickly extract it, but I'll pause here because we are already out of time. Quickly, any questions? Otherwise, we can again start with questions and then continue tomorrow. Okay. If there are no questions, we can start with questions tomorrow. Remind me if I just skip over and stop me and ask questions. Okay. Thank you very much. Bye.